So as you know, you've seen the marks for the tests have been posted. I'm not going to get back to data. I want today's a full block. I want to get um, not only six briefings, but also make a positive report. Couple things though, and again, this is kind of on the heels of what I said before. The reason it took me so long to mark this is because of the question types. In my attempt to read them carefully to try to give as many people as many marks as I possibly could in being fair. It's interesting that, not surprising, but it's still interesting that students that excel in the calculation stuff, the stoichiometry, do this, do this, do this, do this. Or even, this will be on the test, learning, remembering. Those questions were done pretty well. In other words, three most important aspects of the quantum mechanics of the atom. Three things that right out of the book, verbatim, fine. The ones where, or orbital diagram, most of the students did well in that. The electron configurations, most, but not all, most students did well in that. A few issues with negative charge means you're adding electrons, positive means you're taking them away, and from where. But the ones that took me the longest to mark, and I think collectively what most students spent the most time on during the test, was explaining things. So for example, that question, using one well-written sentence, describe what each of the following made to our understanding of the atom. A lot of students wrote a lot of stuff. But one of the things, and it's good practice if you go into post-secondary, you have these things on a test. Answer the question. And then when you're done answering it, shut up. Stop writing. So a lot of what students wrote was correct. It just didn't answer the question. So, for example, if Louis de Broglie, in the context of our understanding of the atom, Louis de Broglie said that was the first to suggest that particles have a wave energy. Okay, I didn't mention the atom. Or Erwin Schrödinger was the first person to mathematically treat the electron as a pure wave. Okay, how does that help us understand the atom? Werner Heisenberg suggested it's impossible to know both where an electron is and where it's going at the same time. Yes. What? So what in terms of the atom? Now that I didn't say memorize. That is my attempt to see if you understand it sufficiently that you can explain it in one well-written sentence. The one sentence part and the well-written part also proved to be a bit challenging. Some students decided that right next to that scientist's name, like Erwin Schrödinger, was the first. Fair enough. But if the W that you use to begin that is a capital letter, that says that's the first word of the sentence. And if that's the first word of the sentence, it isn't a sentence. Some people thought if they put enough commas, it has to be a sentence. That's not true. I didn't take marks off for spelling, which was a good thing because a lot of you can't spell. Little grammar things. A word begins with a vowel, and it's an before it, not a. Like not a orbit, a atom, an orbit, an atom, an electron. Little things, right? Have you guys had your literacy test yet? Did you do that on your literacy test? I hope not. I'm not surprised. It just seems that is more of a challenge than it should otherwise. The question on Broglie's equation. That question began with consider the Broglie's equation. I didn't say in that shows us that electrons have both the particle waves. I just said consider the equation. And as it applies to electrons in atoms. So there's the first two criteria. You're focusing on that equation, electrons in it. Use it to explain how it gives us the clues to the allowed energy states opposed to the boron of the atom. Okay, look at the equation. I didn't tell you what those symbols represented, so a good way to start was the equation tells us that electrons have a wave nature symbolized by lambda. If that's true, then electrons are a wave, and perhaps the only allowed energy states are those in which, in an atom, are those in which we can maintain a standard electron. But you have to tell me that it says that electrons have a wave nature. The second part was, again, using the equation, while we can ignore the wave nature of macroscopic particles, but we can't ignore them when discussing length. Again, look at the equation. There's an inverse relationship between mass and wave length. That inverse relationship is through a very tiny constant. So a good way to start that is because wavelength and mass are inversely related through a very tiny constant. Therein lies the explanation. Any macroscopic object has a mass so big that the wavelength is insignificant. When the gas gets as small as an electron, the wavelength is done. Remember I said what I want you to remember about H, not the number, just that it's really tiny. That was why. Now, all of that was discussed in class, but it wasn't perhaps verbatim. Some of it was, but not all of it was written down. And notice that the room I gave you to answer those questions weren't a whole page. If I gave you a whole page, probably wouldn't use it. But you should be able to answer it relatively succinctly. And then when you're done, stop writing. Some people decided the more stuff they threw at the wall, like we, some of it gets stuck and it would be a correct answer. Don't do that if you don't have, if you can answer the question, shut up. And it doesn't have to be long. Anyway, I will give the test back and we'll go through them. You guys know the marks, and I'm not saying all this because, you know, on average, people did crummy. They didn't. The class average was okay. I just always find it interesting to compare the prowess of students with quantitative chemistry and how well they do their ability to explain things. And sometimes it surprises you. Sometimes the people that don't do so well in the calculation part are really good at the description. And that's nice too. It's just, this test probably more so than any of the ones I've marked up to now, it's taken the longest time. It just says more of the questions that aren't rote memory or calculations. What I want to do now is literally pick up where we left off before we got your professor. We talked about covalent bonds and ionic bonds and bookends and spectra. Where electrons are shared so unequally as to be considered effectively attractive, and where they're considered equally enough that it's quantified sharing. So we're going to begin on page, I believe it's page 309. It is. So the bookends we've talked about are kind of these, where the delta En is 0, that's pure covalent. Well, what does that tell us? Quantum mechanically, it means that the probability for electron location is most likely equidistant between the nuclei. Not 100% of the time, just more probably. If it's up to 0.4, not 0.4, but less than, it's mostly covalent. Meaning there's a little more of a chance that it'd be closer to one nucleus than another, but not so much that we can measure it. So it's mostly covalent. Or as you saw the video, the periodic table, the properties that I have on the board, we talked about percent ionic sharing. When it's more than 1.7, the sharing is effectively unequal enough that the electrons can be considered to be transferred. Then we have ions. And there's that little table of characteristics of ionic bonds that I put a couple of pages earlier. Sharing, there's also a table. But if it's between 0.4 and 1.7, it's still sharing. But it's not unequal enough that we call it ionic, and it's not equal enough that we call it pure covalent. Now the electrons are most probably located closer to the one nucleus, which means we can measure that one end of that bond is a little bit negative because more electrons are in that direction. One end is a little bit positive. A bond dipole is said to exist. And as we're going to learn later on in section 6.5, there's an actual quantitative term we give to that. We call it a dipole bond. And we can calculate it. We can't notice that for this, but we can notice it for this. And why 1.7? Why is that the cutoff? Because at 1.7, the percent ionic character is 51%. More ionic than it is covalent. Greater than 1.7, it's ionic. The type of bond then formed is a polar covalent bond, sharing but unequal sharing. Let's look at an example of a polar covalent bond. When a hydrogen atom having an electronegativity of 2.1 bonds to a chlorine atom with an electronegativity of 3. Remember, chlorine and nitrogen are tied for third. Chlorine is first at 4, oxygen second, 3.5. Chlorine and nitrogen. Difference is 0.9. The electron density, because of that, will be concentrated near the chlorine, given that end of the bond a partial negative charge. Not a full negative charge, just a little bit. And we designate that little bit using the lowercase greek. Already know what the capital is. It's that. It's a capital. This is kind of a greatest kind of squash that tells us it's a little bit. Here's one way of depicting that polar covalent bond, where the electron clouds we hold in the direction of chlorine, and if we pull it away from hydrogen, the sense of bonds are moving positive, sense of negative. Another way to depict it is this. The arrow always faces towards the side with the more electron density. And that little thing tells us here, this is the electropositive side of the bond. That's the electronegative. Now, as long as we're talking about this, notice I only have 2 atoms in this molecule. And as we're going to learn in section 6.5, if we have a 2-atom molecule and that bond is polar, so is the molecule. Now you might ask, how could a bond be polar but the molecule not be? Well, what if we got more than one bond? Let's say we have a polar bond this direction, and the shape of the molecule is such. We got another polar bond in that direction. Bond dipoles cancel each other out. What that means is that this molecule would not tend to stick with uneven distribution of charges. This molecule works because of a molecule of hydrogen chloride. In the vicinity of another hydrogen, you sense a little bit positive. You might expect. And that's part of what we're going to talk about in section 6.5. The title of section 6.5 is the shape and behavior of a molecule. And this is part of the behavior. Where are we going to get the shape from? Well, we're going to get the shape from illustration, which is what 6.4 is about. Okay. So far, we've considered the formation of only one bond per atom in 2 different molecules. There's hydrogen, completely equal sharing. There's hydrogen chloride, polar covalent. Notice that hydrogen and chlorine each require a single electron to become isoelectronic with the absolute gas. And remember, that's the motivation for this thing. Hydrogen case, one more electron will complete its first energy level. When chlorine acquires another electron, it receives a quintet. In each example, the sharing of one pair of valence electrons, whether equal or not, gives each atom the benefit of the extra electron in its formation. Of course, nonmetals sometimes require more than one electron. Chlorine's one away from being like the nearest simple gas, so is hydrogen. But oxygen's two away. Nitrogen's three away. Carbon's four away. So the number of electrons a nonmetal is away from being like the nearest simple gas is the number of bonds that nonmetal has to form. Sometimes it's sharing, sometimes it's getting electrons to form none. The number of electrons required by an atom to achieve the stable outer electron configuration represents the number of covalent bonds the atom must form. Carbon needs 4 more electrons, it has to form 4 bonds if it's going to complete its octet. 4 electrons in the valence shell and 180. Nitrogen needs 3, it's going to need to form 3 covalent bonds. And that was kind of what we did in September. Where we talked about the number of electrons and atoms have to get from table 3. Okay. We can use table 634 to predict formulas of compounds between elements in these families. So that's carbon's family, 14. Electrons needed. That means it's going to have to form 4 bonds. You don't even need to see this in a page. Let's just count it. See. Nitrogen needs to form 3. It's got 5 electrons in its valence shell and wants 3 more, 3 bonds. Every covalent bond, every single covalent bond gives the atom, each of the atoms in the bond the benefit of 1 more electron. 16, 2, 17, oxygen's group, and halogen's group. So let's say we wanted to make a formula of a compound between phosphorus and chlorine. Phosphorus needs 3 electrons. Chlorine needs 1. So this looks a lot like the ionic thing we did before, except there's no charges. 3 here, put the 1 there. We get these. Now, for most covalent compounds, don't reduce the number, if it's possible, to the smallest value. You always have to do it for ionic compounds because the formula is just duration. Most covalent compounds exist as molecules. So as we've said many times, if you were writing a molecule of glucose, C6H12O6, you don't reduce it because it's not a ratio. Where you can reduce it, I'll tell you. But that'll be clearer when we get into Lewis structures. Okay, for now, don't reduce it unless I tell you. Okay? Real simple sample plot. Predict the formula for the compound formed of the following elements combined and determine whether the bonds present are polar covalent, non-polar covalent, or polar covalent. So they're all non-metals. Nitrogen and fluorine. Nitrogen needs 3, fluorine needs 1. It's 4 things. Don't worry about the 3 when you calculate delta E. Just the nitrogen. I can give you one of those, one of those. It's 1.0. Carbon and hydrogen. Carbon needs 4, hydrogen needs 1. That's methane. 0.4, just polar covalent. Silicon and nitrogen. Silicon needs 4, nitrogen needs 3. There's the formula. 1.2. Notice that carbon and sulfur are different elements, but they have the same electronegativity. And this one you do reduce, and we're going to see why. For example, in section 6.5, that's because 2 double bonds. That's one of the interesting things about carbon. Not the only, but one of them. Carbon needs 4 more electrons, but it satisfies that octet in any combination. It could be 4 single bonds. It could be 1 single bond and a triple bond. It could be a double bond and 2 singles. It could be 2 double bonds. And that variety of bonding is one of the reasons organic chemistry is so complicated. Which reminds me, we're April 20th. Have you guys looked at the schedule for next week? You know what happens Tuesday? Housekeepers. Friday is Greek Olympics. Thursday, Wednesday is advisory. So next week is pretty much shot. This week, even. I see you guys Wednesday, fine, that's COE. But it's not just regular ceiling, it's something with mock interval. Thursday, we have a late start. Why? I have no idea. I think Friday is a regular day. My point is, in terms of number of days till the end of the school, and then when we get to May, then there's a Mother's Day Mass. Then there's the long weekend, which by the way is a 4-day long weekend, not 3, because we get Founder's Day, which I believe is the 22nd. We don't have that amount of time till we're done. So I've been forced to make an executive decision vis-a-vis our test schedule. I very much believe that we're not going to have time for a chapter 6 test. I don't know if that's good news or bad news. Think of what we did for the test. Think of what I did for the test we just wrote. We took a whole class for review, obviously a whole class to write it. We're going to take the majority of Wednesday to go through the test 3 classes. With the amount of time we have left, that's a luxury that is exactly that. It's a luxury. So that means the important stuff of 6 is going to be on the final exam. I can't do that in fairness without at least telling you what types of questions I could ask you. So in lieu of a review class test going through the test, I will take a chunk at the end of 6 to show you what types of questions you should be ready for. Okay, I might do a few multiple choice. I'll definitely do a written response. Remember when we did the mold chapter, I said, remember this table? Formula, molar mass of the compound, and then convert moles to grams or grams per mole. Remember that? There's going to be a similar table, which will summarize 6.4 and 6.5. But I'll give you as specific an exam outline as I can. Obviously, if we don't have time for a test on chapter 6, I have to include some of the salient stuff in the final exam. But I'll introduce it sufficiently that when you see it, it's not going to be, oh my God, how do I do this? I'm doing that because I want to get into chapter 8. I want to get a good chunk of organic chemistry done. You're never going to see organic chemistry in high school again. So that's why it's kind of important to talk about it in grade 11. And if the 3 classes that we would have otherwise taken, review, write, and go through the chapter 6 test, is actually now given back to us. There's a lab in chapter 8. It's an insert in the book I added, but it takes 2 or 3 classes. And it's model building. But you can't do it until we've done at least section 8.1. So I want to get that in before the end of the year. Now that's a lot. What I probably can't guarantee is multiple review classes before the final exam. But well in advance of the final exam, I will give you an exam. And I can't, in a 2-hour final, give you everything you've done. There's just no time. So I will focus on what I consider to be the most important stuff. And if you look at the major topics we've gone through, you probably can get an idea what the focus is going to be. And the first half of the year ended with stoichiometry. So you can be quite sure there's going to be something in stoichiometry. But I'll tell you, will it be limiting reactive? Will it be straight stoichiometry? That stuff like that. You can be sure that there's going to be some quantum mechanics. And as you're going to see, you can be sure there's going to be something on 6.4 and 6.5. Right? I'm not saying that to ruin anyone's day. I'm just orienting for you, okay? Now, in terms of some of the project problems, consider the delta EN values and pair up the elements aluminum, chlorine, nitrogen, and sodium. Write the formula for the types of compounds identified. Specify each choice by showing the appropriate delta EN. So a compound with an ionic bond. Compound has to be 2 different elements. The ionic bond has to have a delta E greater than 1.7. So it's going to start with sodium. Pick sodium chloride. That's a 1-to-1 ratio easily. And 3.0 minus 0.9 is 2.1, including ion. A compound with a polar covalent, two different elements. Obviously, you can't have sodium. So what would be a compound with a polar covalent? Okay, let's look at the two non-hydrogen and fluorine. If you make a compound between nitrogen and chlorine that has a polar covalent function, what's the delta EN? What's the electronegativity of nitrogen? 3. What's the electronegativity of chlorine? 3. That's a covalent compound, but it's not polar covalent. Well, the only other element is aluminum. Aluminum is a metal. So remember, whether it's covalent or ionic is not necessarily metal, non-metal, or two non-metals. Aluminum has an electronegativity of 1.5, right? Nitrogen and chlorine also, because they have the same electronegativity, that delta EN is non-ionic. If you want a 1-to-1 ratio, aluminum and nitrogen, delta EN is 1.5. It's getting close towards ionic, but it isn't. Just because it's a metal and non-metal doesn't mean it's ionic. If it's ionic, it has to be metal non-metal. But just throw the metal and non-metal. Delta EN is going to be bigger than 1.7. A compound with a non-polar covalent bond. Two different elements, that's got to be aluminum and nitrogen. Or sorry, nitrogen and chlorine. And that formula would be NCO because nitrogen needs 3, chlorine needs 4. Calculate the delta EN values for the bonds in the following compounds and arrange the compounds in order for yields containing bonds with the electrons are shared most equally, smallest delta EN. Delta EN is curious. So obviously the smallest that goes in. That looks like an element. You guys can do that. Number 3 is some covalent, some pure covalent, some polar covalent, some ionic. Again, you guys can do all that. And wherever it says atom possessing the greater electron density, that's the one with the higher electronegativity, if there is one. Notice that in carbon and sulfur, there isn't. Carbon has 2.5, sulfur has 2.5. So atom possessing greater electron density, nitrogen. That's pretty much the end of the section. And this is something I referred to earlier in the year. Remember when Gary decided that you could replace covalent with molecular? Covalent and molecular are not synonymous. Most covalent compounds exist as molecules, like water. Some covalent compounds don't exist as separate molecules. Remember that ionic compounds are solid at room temp and have high melting points. This results from the vast number of interionic fuses locking all the ions together in place. So in a crystal lattice, the ionic bonds, chemical bonds, extend in 3 dimensions. That huge amount of attractive forces is why it takes so much energy to melt. 801 degrees Celsius. Covalent compounds involve electron sharing. So there's no ions attracting each other. But that doesn't mean that covalent bonds are weaker than ionic bonds. And I've used an extreme example today. Methane is what primary gas that comes out of here. Methane has a melting temperature about 1,000 degrees lower than this. But some students think, well, that must mean the bonds in methane, the CH4, the CH bonds, are weaker than the ionic bonds. That's not true at all. The difference is when I melt a covalent compound that exists as molecules, I don't pull atoms apart inside them. I pull molecules. So the only attractive force I'm overcoming is what's called intermolecular. Those are chemical bonds. So if I'm using this and this to compare the strengths of the bonds, that's apples and oranges. Here I'm breaking chemical bonds. Here I'm not. I'm just pulling molecules. So again, this is because no chemical bonds are broken where when met they were any molecular. Instead, weak internal molecular bonds. Now, if I could find a covalent compound that didn't exist as molecules, if I could find a covalent compound that was kind of like this, where all the atoms were stuck together covalently in a three-dimensional structure, then that's apples and apples. And a great example of that is quartz. The formula for quartz is SiO2, but there's no molecule of SiO2. That's a ratio. That's because the silicon and oxygen exist in a 1:2 ratio in what's called a network covalent salt. You grind that up, you get sand. That's what sand is on the beach. Okay? But if you look at that, there's no molecule. So if I want to melt that, I got to break chemical bonds in 3 dimensions, just like I have to do here. When the melting temperature, silicon dioxide is almost twice that. So important. Now you're comparing apples to apples. Okay? In this case, the melting point does reflect the strength of the bond. And it shows us that covalent bonds are every bit as strong as ionic bonds, if not stronger. Now, more than just the fact that there's no molecules affects the strength. It also has to do with the stability of the crystal. But at least now, if you're going to melt that, you got to break chemical bonds. Not so if you're melting or boiling something that's held together by intermolecular forces. Okay. Don't worry about the activity. I thought it was kind of clever. I thought because polar bonds are a bit ionic and a bit covalent, I thought, okay, green and blue, or yellow and blue make green, red and blue make purple, and green and blue or yellow and blue make green. I thought, okay, let's take care of all of them. So I took the halogen in the first 3 periods, chlorine, fluorine, and bromine. And the idea is write the formula for the compound formed when that halogen forms bonds with the other members of that period. And around that formula, color it in depending on the nature of the bond. Yes. Can't hear you. Yes. So obviously fluorine and fluorine, delta En is 0. So when I said, okay, blue and yellow makes green. Blue and red makes purple. Red and yellow makes orange. That would be a good combination. Look really good on a piece of paper. Jerry said, no, that's too complicated. And I acquiesced, as I shouldn't have. So I said, fine, blue and yellow. So if the bond is pure ionic or ionic, write it yellow. If it's pure covalent, put it blue. And if it's in between, color it green. So the idea is you kind of go from yellow to green. Yellow, orange to red, and maybe blue, purple, red. Anyway, I'm not a scientist. I just wish I would agree to the pressure exerted by Sharon. Notice that there's no calculations in the review. There may be a delta En calculation, but again, these questions are different. Now, there will be questions like this on the final exam. I'm not going to make up the majority of the final exam, but it's just something to keep in mind where explanation is where you get the grades rather than just your calculator. And I will give you a pretty specific exam of it. Okay, I'm not going to say I'll give you something from chapter 5. I'll tell you what from chapter 5. Okay. Not going to be any surprises based on the level of detail. I want to start in now with section 6. Some of you may remember that fluid structures were at least mentioned in Science 10. They weren't mentioned well, they weren't explained, nor was the perfect for doing it. We're going to use Lewis structures for one reason, to predict the shapes of molecules. Why do we want to know that? Because we want to predict behavior. And if you look at the title for section 6.5, it's exactly that. The shape and behavior of molecules. Lewis structures is two-dimensional series of dots and lines and centers. But if you draw them properly, they can be used to pretty accurately predict three-dimensional shapes without the need for complicated bonding theories. Those bonding theories are out there. It's just that a lot of times we don't need them. As you learned earlier in atoms, valence electrons are the outermost electrons. These are the electrons involved in chemical bonds. In valence electrons is chemistry. This means that in terms of chemical behavior, they're the only one we really need to worry about. In 1916, the American chemist Gilbert Lewis devised a system of representing the atoms of the elements based only on the number of valence electrons they possess, because that's all that matters in terms of their behavior. This notation system uses each element symbol to represent everything except the valence electrons. In other words, the nucleus and all of the inner or core electrons, the ones that aren't involved in chemical changes. And then around that symbol, you put a series of dots. The notation is a simple and useful way to represent atoms, and it serves as a foundation to help us understand chemical behavior, compound structure, without the need for sophisticated nomenclature. The method that we're going to use to accomplish that, it's given a name. It's called Vesper theory. You don't need to remember it yet, but VSEP. It sounds complicated, but it's based on one real simple thing. Valence shell electron pairs repel each other. And based on those electron pairs on the outside repelling each other, you can pretty accurately predict the shapes of the molecules that are going to result from all that information. Now, were there other theories out there? Yeah. I put them in the AP book. For some reason, Lionel left one of them in this book. You won't have to worry about it. So where in chapter 6 are we stopping? We're stopping at the bottom of page 345. So you don't have to worry about valence bond theory, hybrid orbitals. You don't have to worry about that. Okay? That's not the only thing. There's also molecular orbital theory. There's crystal field theory. You don't have to worry about any. This is all we're doing. And there's a memory component to it, but it's not hard. Okay? Section 6.4 is only about Lewis structures. We're going to use Lewis structures in this to predict shapes of molecules. We'll begin by discussing Lewis structures for individual atoms and ions, then expand our discussion to include molecular compounds and polyatomic acids. The first thing you need to know to draw a Lewis structure is how many valence electrons are there. We're only going to focus on the main group elements. We're not focusing on the transition groups. So that it's the S block and the P block. There's a number of valence electrons, count consecutively. Group 1 has 1, group 2 has 2, 13 has 3, etc., all the way up to 11. And there's the electron configuration as per quantum mechanics. Draw a Lewis structure for an atom, follow these steps. And they're hardly even steps. For hydrogen, place a single dot next to the symbol. Doesn't matter where the dot goes, as long as there's just one of them. There's the Lewis structure for hydrogen. So here. Helium, not just two dots, but here. Helium's the only atom for which the 2 electrons are paired. For second period elements and beyond, that is beginning with lithium and bigger. For each valence electron present, place 1 dot around the symbol at one of the four positions of the compass. West, east, north, or south. It doesn't matter which node you start with. So for example, we were going to do beryllium. Beryllium has two dots. So that's like two dots could be there, 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 there. Doesn't matter. As long as it's just two dots. If you keep going, let's say from beryllium to boron, three dots, which would be there, 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 doesn't matter, three dots. Carbon, we have four dots. Once compass positions are populated before the corners is crossed. Any more electrons that are there, only then do you begin pairing them up. Nitrogen, 5 valence electrons with 1, 2. No matter where the pair is. All that matters is we've got one pair, 3 electrons by themselves. There's the first 3 periods. Notice that now it's family in 3 respects. The only creativity is simple. It's basically 3 senses. So that symbol Cl for chlorine means a nucleus, 17 protons, 18 neutrons. 2 electrons in the first energy level, 8 electrons in the second. Gilbert called that the kernel of the atom. It's the core. It's what's wrapped in those square brackets. So those 10 electrons never take part in chemistry. All that matters is what's on the outside. Notice the dot by itself is here. It could be here, here, or here. It doesn't matter. Okay. Now, a couple things are obvious from that diagram, that table. As each element in the family has the same number of valence electrons, the Lewis structure of those elements has the same number of dots. Example group 15, nitrogen. 2. Any symbol in group 15 could go there and out to be the Lewis structure. Nitrogen, phosphorus, arsen, and this one. All that matters is the number of dots on the outside. That's obvious. Number 2 may not be. For metals, the total number of dots, what do metals do when they take part in chemistry? They give electrons. The total number of dots represents the number of electrons that each of those metal atoms will lose when forming a cavity. So lithium's got 1 dot, it'll lose 1 electron. When that electron comes away, that also tells us the charge on the ion, 1 plus. Beryllium will be 2 plus, magnesium will be the 2 plus, aluminum will be 3 plus. So for a metal, the number of dots tells us how many electrons are going to be lost when that cation forms. And when we draw a Lewis structure for an ion, we wrap it in square brackets and put the charge outside. For metals, there will be no dots inside those square brackets. In a correctly drawn structure for a non-metal, the number of unpaired dots are the number of electrons that atom has to share, be like the nearest noble gas, or get if it reacts with the metal in forming an atom. So again, back to nitrogen. Nitrogen's Lewis structure is this. That tells us if nitrogen reacts with a non-metal, it's got to form 3 covalent bonds. If it reacts with the metal, it's got to gain 3 more electrons to form an ion. And again, it doesn't matter where those electrons are by themselves. It just matters that they're big. Okay. Now, we're going to draw Lewis structures of some ions, but we don't really use Lewis structures much when we're talking about ionic compounds. And we did this in Science 10. But Lewis structures on their own is not really that useful. The real purpose behind Lewis structures is to predict shapes of molecules. And ionic compounds don't exist. But if we wanted to draw the Lewis diagram for a sodium ion, start with the atom. Ion, it's no dots. One dot that we take away is the magnitude of the positive charge. Chlorine. Chlorine has 7. 1, 2, 3, 4, 5, 6, 7. That lone electron tells us when it reacts with the metal, it's going to gain 1 more electron. When it does, 1 minus. So if someone asks, what's the Lewis representation for sodium chloride? That's not the formula of duration. So we can't use the formula to do anything in terms of shape. This is with the ions, but that doesn't tell us. We could write it, it's just that it doesn't give us a lot of information. And obviously we could extrapolate to a few more examples, and we will. What do the dots in a Lewis structure represent? Valence electrons. What are the total number of dots present in a Lewis structure for the metals 1, 2, and 13 tell us about the cation they form? The number of dots is the charge of the cation, because that's the number of electrons are going to go away. Ergo, there are no dots in the square brackets, because they're all gone. Wrap the ion in square brackets, put the charge outside. If we were going to write the Lewis structure for an aluminum ion, start with the atom. 8 dots are there. 1, 3. That means the charge on the cation, and all those are gone. The Lewis structure for nitrogen, phosphorus, and antimony include 1 pair of dots and 3 unpaired dots. How many electrons do these atoms require for the sodium octet? 3. The number of unpaired electrons. Electrons don't like to be unpaired. They exist in pairs. Now, those electrons could come from reacting with a metal where they gain electrons, or they could come from reacting with non-metal where they share, but they need 3. Draw the Lewis structures for the representative elements, the main group, belonging to period 4. It's easy. Just change the symbols on the previous table and put, so underneath sodium is potassium, underneath magnesium is calcium, all the way across. The number of dots stay exactly the same. If we wanted to do the 5th period, erase K for potassium, put in rubidium. Instead of calcium, put strontium. That's the idea. And I ask you to do that here. The only thing that changes is the symbols. The dots stay the same. Write the Lewis structures for the following atoms and ions. Well, obviously, if there's no charge, brackets, variance of metal. Electrons there. So that is aluminum 3+, no dots. Bismuth, no charge, so there's no brackets. Bismuth is at the bottom of nitrogen. 1, 2, 3. Iodide anion. Iodine has 7 valence electrons, but an iodide anion One, two, three, 4, 5, 6, 8. It's 1 valence. So the Lewis structure for non-metal ions has dots. The structure for metal ions don't. Tellurium is underneath selenium, which is underneath sulfur, which is underneath oxygen. 6 valence electron, 1, 2, 3, 4, 5, 6. And wherever the 2 pairs, where you want them to go, put them here, here. That tells us that tellurium needs 2 electrons from somewhere. You like to hear something else. Number 3, all of them are ions, so all of them should have square brackets and charges outside. So calcium, there's two dots, but it's a metal. You give both of those away. So 2 plus. Selenium's a non-metal, but as an ion, it needs 2 electrons to become krypton. So it's got 6, 1, 2, 3, 4, 6. Put 2 more there. Brackets. Gallium's a metal, it's underneath aluminum. As an atom, it has 4 and 3 all the way. Make sure the 3 plus subsides for that. Arsenic is underneath phosphorus on nitrogen. As an atom, arsenic is 1, 2, 3, 5. If it's 3 more, give it 3, and also try to give it that magnitude. Now that's kind of science 10, right? This may seem like an odd way to start this paragraph. Each of the pages in this book is a flat surface, and any diagrams or images that you see on these pages can only be two-dimensional representations of the real three-dimensional world. Three-dimensional world is made up of ionic and covalent compounds that also exist in 3 dimensions. Understanding their shapes is a very important part of explaining and predicting their behavior. Ionic compounds normally exist as ordered 3-dimensional arrays of cations and anions called crystal lattices. The arrangement of ions maximizes the attractions between the oppositely charged ions and minimizes the repulsion. That's how the ions pack in the most efficient way. And you guys have seen both in the book and held up the crystal lattice. We don't really need nor use Lewis structure to create these things. When molecules form, their 3-dimensional shapes are also governed by the attractive and repulsive forces that exist within them. The first step in visualizing the 3-dimensional shape of a molecule is to convert its molecular formula into a 2-dimensional Lewis structure. There's no attempt to make the Lewis diagram look 3-dimensional. We're going to use it for that, but you don't have to worry about perspective in a Lewis structure. Okay. One of the tables I'm going to give you on your final exam, which is what I will go through when we're done chapter 6. The table will have formula, and what you guys have to draw based on the formula is the Lewis structure, which we're going to start in a few minutes. Based on the Lewis structure, you're going to look at it, and you're going to assign it a category. And you'll hear categories in 6.5 like AX2, AX3, AX2E, AX3, AX2E2, all of those things. Each one of those categories is based on the Lewis structure. And once you know the category, then you can predict a shape. And if you're interested in what that looks like, if you flip ahead in the section 6.5, for example, look in the bottom of page 332, and then over to 333, and then 334, and 335. Those are the shapes that the Lewis structure will predict. And once you know the shape, then you'll be able to say something about the behavior. And that's what the table will look like. The table that I'm referring to, a version of it would be on the bottom of page 337. Page 337. We're not there yet, so this isn't going to make a lot of sense, but just to give you a clue where we're going. So on the left-hand side, you have a chemical pending. I'll give you that. Based on a formula, you draw the Lewis structure. The category that I'm talking about is called AXMEN notation. You give it one of those, and based on whatever's in the little box in the middle, then you name and draw the shape. Now, it sounds hard. It's not. It's really easy. The shape is really based on a very simple thing. That electron pairs repel each other. Okay? And they want to get out of each other's way. And when they do that, they adopt specific shapes. Now you think, well, that still sounds kind of hard. Well, if you blew up a whole bunch of balloons and tied them together, we're going to do it for you. Look in the bottom of 231. We take 2, 3, 4, 5, and 6 balloons together. Assuming all the balloons are the same size, that's the shape they're going to occupy. Electron clouds do the same thing. And we're going to name each of those shapes. It's actually that easy. Theory is called valence shell electron pair repulsion theory. VSEPR theory for short. It just means valence shell electron pairs repel each other. And that gives us these shapes. Now, we're going to get to those shapes by looking at the dots and lines we see on a two-dimensional illusion. And that's kind of where we're going. Okay? Now, the simplest example of a Lewis structure is a diatomic molecule. Now, notice, I'll build that for you, but notice that the action covalent bond, pairing electrons between the atoms, isn't a electron, it's a bond. The reason we do that in the structure, in terms of predicting shape, electrons in a bond take up less room because they're sucked between two nuclei. And the cloud of electrons is held tighter when there's two positive charges attracting. Electron pairs out here take up more room. They're really attracted to one nucleus. So whether it's a lone pair of electrons, or a bonding pair match, if I wanted to draw that, now obviously chlorines aren't two different colors, but if I draw a chlorine atom, 1, 2, 3, 4, 5, 6, 7, the electron that I leave by itself is here because I'm going to put the other chlorine here. I need one more electron because I have one dot. The other chlorine, 1, 2, 3, 4, 7. Each chlorine has the benefit of that extra electron. So each chlorine has its oxide saturation. But when I'm done, that's kind of what we did in Science 10. Steps attached to drawing a Lewis structure, though, for maybe a more complicated species, have to be followed in a different order. And that's what we're going to do here. We're going to talk about drawing a Lewis structure for a molecule. And we'll do ions later. As with any new procedure, learning to draw Lewis diagrams for molecules is easier if you follow a series of steps. Remember when we did stoichiometry, we went through the steps. Automotive. When you're talking about empirical formula, what do you do? What are the steps? When we're talking about living reactors, what do you do? Same thing here. It might seem onerous at first. You do a few of them, you're not even going to need to worry about what steps you do. So let's draw the Lewis structure for NCl3. So imagine in the table that I referred to, you saw on the left-hand side in that column, box, NCl3. You then follow a series of steps to fill in the next box, the Lewis structure. First step in drawing a Lewis structure is to count the total number of valence electrons. So nitrogen has 5. Each halogen has 7, 26. When you're done, you got to be able to count for all 26 of those electrons, whether there's lines or dots. Notice that this is an even number, which will be true for all of the examples you'll see. There are a few cases where odd numbers of electrons exist, but those species are very unstable. We call them free radicals. They're not good. They're oxidizers. They're oxidizing agents. Electrons love to be paired. From a quantum mechanical perspective, it's really stable to have those two spins opposite, reducing that orbital to having no magnetic field. And Lewis was the first person to recognize that there's something important about paired electrons, long before he knew about spins. Okay. So if you count electrons and you get an odd number, you goofed up. Go back and fix it. It has to be even, which is another way of saying that every Lewis diagram is going to have paired electrons, either as lines or dots. Step 2, construct the skeleton of the molecule. Now, you don't, over there with the chlorine, you put the line in at the end. Here, putting the lines in at the beginning. So let's just do step 1, number of valence electrons, 5 plus 7. Step 2 is to construct the most likely skeleton. Like which atoms are most likely stuck to which atoms. To generate the most likely skeleton, the following set of guidelines will be of great help. None of them are really surprises. And you're not going to have to go back and refer to this when you draw the skeleton. You'll be able to do this very quickly. The guidelines are based on numerous empirical observations, that's just from lab analysis, and hold true for the vast majority of molecules. They also correspond to what you would expect, given the configurations, that is, how many electrons an atom needs, and electronegativities. They may seem difficult to remember at first, but you're not going to need to use all of them, actually, for any molecule that you draw. And as with any new skill, the steps will become more familiar with practice. So if the general formula for the compound is this, which by the way this is, then A is going to be in the middle. So nitrogen will be in the middle. The chlorines are going to be around. And notice it'll also be the one with the lower group number. That makes sense, because nitrogen needs 3 electrons, chlorine only needs 1. 15 or 17. And usually, but not always, the central atom will have the lower electronegativity. Nitrogen is further to the left than chlorine, but remember they're tied for third at 3.0. Hydrogen atoms, we don't have any hydrogen here, but hydrogen atoms form only one bond. So when you're drawing a skeleton with hydrogen, there shouldn't be any more than one line connected to an H. Why can hydrogen just form one bond? It has 1 electron. When it gets 1 more, which it will in a bond, not only is its valence shell filled, but so is the first energy. So it doesn't have room for any more than 2 electrons. So if you have H and 2 lines coming from it, something's wrong. Okay. Fluorine atoms always form only one bond. Again, for the same reason. When fluorine gets 1 more electrons, the second energy level is filled. There's no room for any more. So if you ever have 2 lines coming from a fluorine, it's wrong. Now, all halogens don't necessarily emit. Fluorine is the only one that can only have 1 bond. Other halogens usually form 1 bond, which makes sense because they need 1 electron to ignite the noble gas. But sometimes they can have more than 1 line coming from. But that'll only happen if the halogens in the diagram are the central atoms and they have to be bonded to either smaller halogens or oxygen. Well, it can't be fluorine because there's no halogen smaller than fluorine. But chlorine could sometimes be a central atom. And there could be oxygens around it. Why do you think chlorine has the potential to have more than 1 bond? Even though it only needs 1 more to be like the nearest smaller. Chlorine's in the 3rd energy level, right? How many electrons can we fit in the 3rd energy? 2n squared. N is 3. Squared is 9 times 2 is 18. Chlorine has 7 electrons in its other energy. There's room for 11. So elements in the third period and higher, we're going to learn, can sometimes have expanded octets. Because there's room for it. There's the D supplement. But that never happens with group 3. Okay? And we'll see this when we get into some of these diagrams. Oxygen normally forms 2 bonds. We know that. It needs 2 electrons. That makes sense. But it doesn't like to stick to itself. So when you're drawing a skeleton, let's say for CO3, the carbonate atom, don't put the oxygens together. They don't like to stick to themselves. The only time that happens is if it's in a compound with peroxide. In peroxide, the oxygen sticks to itself. But except for that, don't connect oxygen to oxygen. Nitrogen normally forms 3, makes sense, it needs 3 electrons. Carbon normally forms 4 for the same reason. Avoid creating rings. Rings can form, but the only element that loves to do it is carbon. The other elements don't usually. In a little limited cases, sulfur is S8, it's kind of a ring. But unless you're told you don't, well, gee, I'll put a ring in here. That's uncommon unless it's for carbon. We'll talk about all of that when we get to organic chemistry. That's chapter 8. So if we look at those guidelines for a skeleton, we can realize that the most likely skeleton is that. Let's construct a skeleton. And again, we could put chlorine there, chlorine there, chlorine here, it doesn't matter. Where the chlorines go is relevant. Matters is now it's at all of the guidelines. That's AX. That N there tells us that's probably the central atom that's around. Chlorine has 3 bonds, chlorine has 1 bond, nitrogen has 3. That makes the most sense. And it goes without saying, but make sure that what you have in the skeleton matches the number of atoms in the form. You need 3 chlorines and 1 nitrogen. Once we've constructed the skeleton, remember that every line we draw represents 2 electrons. So now we have to count the number of valence electrons used to construct the skeleton and subtract them from what we have to see what we got left over. So 2 there, 2 there, 2 there. So 6 electrons that we used, right? I'm just following the steps. To construct the skeleton, we've used 6. That means we have 20 left. And when we're done, all of those 20 have to be accounted for. Consider that each line drawn represents a pair of bonding electrons. So in this case, the number of valence electrons remaining is 20. Step 4. Assume that all of the atoms in the molecule in the octet unit, except obviously for hydrogen. And based on that, determine the number of additional valence electrons required beyond the ones already there. All of those atoms that require stable octet. So for example, if you look at chlorine, right now it's associated with 2, right? But the benefit of 2 electrons for that line really needs that. And if it needs 8, it needs 6 more, right? So does that, and so does that. So each chlorine needs 6 more, that's 18. Nitrogen needs 2 more, it's 20. So what we need and what we have is an agreement. Compare the number of valence electrons available from step 3 to the number of valence electrons needed. If those 2 numbers match, pair up the electrons, beginning with the peripheral atoms and ending with the central atom. Put them where they're needed. So don't start with that. Start with these. If there's something that's going to violate the octet rule, it'll never get through. Always satisfy these first. So each chlorine needs 6, So we got 20 left, we got 20 needed. So from where they're needed. 2, 6. And don't just go 1, 2, 3, 4, 5, 6. 3 new pairs. So that would be 2, 6, 6. That's 18. 20. Now, when you look at the final diagram, you count all 26 electrons. 6, 8. That's the first thing. What you have and what you need is a matchup. Second thing, it's every electron in this, it's every element in the structure associated with the same number of electrons as the nearest normal gas. If it is, and everything obeys the octet rule, and it is. For all the electrons arranged in pairs. And the number of atoms in this fence, the number of atoms in this. The answer is yes to all of them. You're right. Okay. At this point, consider the following. A peripheral or surrounding atom, in this case the gluon, will never violate the octet rule.
Afternoon, staff and students. The first show of the audition is today at lunch. The show will begin at 12:40. Please come to the drama room straight away. Thank you. Also, junior dance tickets are being sold at lunch today in the cafe. Make sure to stop by. Now let us prepare ourselves for grace before lunch. In the name of the Father, Son, and the Holy Spirit. Bless us, O Lord, and these your gifts, which we are about to receive from your bounty, through Christ our Lord. Amen. St. Thomas More, Blessed Edmund Rice, live Jesus in our hearts. In the name of the Father, the Son, and the Holy Spirit. Amen.
So these are things about the octet rule. Peripheral atoms never violate. Central atoms can, but only if an atom has more than 8 valence electrons, we call it an expanded octet. It has to be elements belonging to the 3 atom. Because you have the D sublevel there. And it's in the second one. Elements that don't have 8, that don't have enough, are these elements. So beryllium or boron or aluminum form the covalent compound, and they share every one of the valence electrons they have. They still can't get 8. So beryllium, it shares one, they don't get 2. Boron has 3, it shares all of those, it's 6. That means it's an incomplete octet. That happens, but it can't be a peripheral atom. That's why we always start from the else. For Wednesday, I'm going to spend probably the majority of Wednesday going through the test. But if you guys would read to, well, the bottom of 321, have a look at the quick check and the sample problem and try the practice problems on the top of 322. Okay? I'm going to do my level best to finish this section by Friday. I think Friday's a regular day, which means next week I might talk a little bit about what I'm gonna how I'm gonna use Lewis diagrams on the final exam, but I'm writing this in. And then after 6, no test, right into organic chemistry chapter. Okay. And we don't have that much time, so it is what it is. I'll see you guys Wednesday.